In this section, we'll talk about inverse trigonometric functions and how they can be used to find certain integrals. So the derivatives of the 6 inverse trigonometric functions fall into 3 pairs. In each pair, the derivative of one function is the negative of the other. For example, the derivative of arcsine of x is 1 over square root of 1 minus x squared, and the derivative of the arc cosine of x is negative 1 over square root of 1 minus x squared. When listing the antiderivative that corresponds to each of the inverse trigonometric functions, we need to use only one member from each pair. So it is conventional to use arcsine of x as the antiderivative of 1 over square root of 1 minus x squared rather than negative arc cosine of x. Both of these are correct, though, as an antiderivative of 1 over square root of 1 minus x squared. So in the following theorem, we see some integrals that involve inverse trigonometric functions. So we basically saw the first one already. So if u is a differentiable function of x and a is a constant, then the antiderivative of 1 over square root of a squared minus u squared du is the arcsine of u over a plus a constant of integration. And so we also have an antiderivative involving 1 over a squared plus u squared, and we have an antiderivative involving 1 over u times square root of u squared minus a squared. So it's very important when you use these rules, and by the way, these rules will be on the handout that you get for exam 1. What is important to realize is that a is a constant, and u is a variable. So when you're looking at your integrals, you see that a squared minus u squared and u squared minus a squared, that looks a lot like each other. But for the first integral, you have a constant squared minus a variable squared. And for the this third integral, you have a variable squared minus a constant squared. So let's do some examples. In the first example, we're asked to find the antiderivative of 1 over square root of 4 minus x squared. Now, first of all, let's see what is the constant, what is the variable. So under the square root, we see that we have a constant here and a variable here. So u is the variable and a is the constant. So this is not of the form 3. And we're also missing a variable in front there. So we're of this form. So we have to use theorem 5.19.1. So this is an example of having to use theorem 5.19, the first part. And when you look at the constant, that is your a squared. So what we see here is that a squared equals 4. And so that means that a could be plus or minus 2, but in this theorem, a is always positive, so it follows that a equals 2. And then the variable here is x, and that plays the role of u. So u is equal to x in that theorem 5.19.1. So we can rewrite this integral as the integral of dx becomes du. So we can change that here. Let's make that du. And then over the square root of 2 squared minus u squared. Squared minus u squared. And if you don't like to write it like this, you're kind of confused by that du, you could also just write it as 1 over and then put the du at the end. Okay, so this integral, by that theorem, is then the arc sine of u over a. So the answer here is arc sine of u over a. So u here, and then a is 2. So it's the arc sine of u over 2. And then, of course, we have our constant of integration. And since u equals x, we just have arc sine of x over 2 plus c, and that is our final answer. Now for the other example, we're looking at an integral of the form du over a squared plus u squared. But we'll have to do a little bit more work here. So recognize that this is theorem 5.19.2, and now we have a squared plus u squared. So a is the constant, so we have that a squared equals 2, and we have that u squared equals 9x squared. So now if we solve that for a and u, then we see that a is the square root of 2 and u equals 3x, right? If you square u, you get 3x. Now, this is a substitution that we're going to apply to this integral. So what we always do with these types of substitutions is we find du dx that equals 3. So du equals 3 dx, or 1/3 du equals dx. So that's the substitution we're going to apply in this example. And so what does our integral turn into? So it's the integral of, and then I'm going to write 1 over, and then we have square root of 2 squared plus, and then I have u squared. So it's square root of 2 and then u squared. That's my denominator. And then I have my dx, which I can put behind at the end. That is 1/3 du. So when I take a look at that integral, I can take the 1/3 outside. That's a constant multiple. And then I have 1 over square root of 2 squared plus u squared du. And now I'm going to look at theorem 5.19.2, and I see that gives me as an integral 1 over a. So that's 1 over square root of 2 times the arctan of u over a. So u over a, which is u over square root of 2. And then plus my constant of integration. And so finally, what I have to do is I write that as 1 over 3 times square root of 2. And you don't have to worry about like getting that square root out of the denominator. So I'm perfectly fine with leaving it like this. And then times the arctan. And then the substitution that we made was u equals 3x. So this u here can be replaced by 3x. And then we're still dividing by our square root of 2. We add a constant of integration, and that is our final answer.